Mr. B. Dhanasegar is working as a lecturer in Department of Information Technology, Anna University, Chennai. He finished his MCA from Urumu Dhanalakshmi College, Bharatidasan University. He finished his ME in Computer Science and Engineering from College of Engineering, Anna University. His areas of interest are multi-core programming and architecture, programming models, compiler, automata theory, cryptography, and algorithms. He is an expert in subjects like compiler design, formal languages and automata theory, analysis of algorithms. His research area is code generation for multi-core architecture.
Welcome to the UGC lecture series. The subject we are having is the theory of computation. This is the second episode of the lecture series. Let me start with a recap of the episode 1. We have seen what is the definition for formal language. Basically it is derived from a finite set of symbols, and then we have seen the various elements of the formal languages, like what is definition for a symbol and what is an alphabet, what is the language, the strings, string length, etc. And then we have seen what is definition for the automata theory. Actually it is a study of abstract machines, and abstract machine is nothing but the theory of model. And as far as this lecture is concerned, we are going to have the definition of regular languages, that is normally going to be the basic class of language in the Chomsky hierarchy. And then we have the description about that is the irregular languages, that is how they are described, what are the tools used for that and their relationships. And then we will study about the finite automata. We have actually two classes of finite automata. One is the deterministic version and another one is going to be the non-deterministic version. Okay, let us see the definition of regular languages. It is the most basic class of the language as far as the Chomsky hierarchy is concerned. The Chomsky hierarchy actually is talking about the entire class of languages in the formal language. We have like regular, then context free, then context sensitive, and keep going. So here we have the definition of the regular languages. So you can see that the most restricted and simplest as far as the norm Chomsky hierarchy is concerned. So this is the most simplest one. If you are thinking about the complicated, like the recursively enumerable languages, they will be coming under the top of the entire hierarchy. But this is going to be the one which is available in the basic case. And how it is going to be described? So it is described using the regular expressions. So regular expression is just like an expression kind of thing. Normally we will be using for searching, pattern matching, and so many things. Like suppose if I am interested in listing the files which are starting with A, then I will have a pattern like A followed by star dot followed by whatever the extension, whatever we want to have. So that is a simple example for a regular expression. So it is just used for pattern matching. So the pattern or the entire class of strings which we want to recognize will be described by using this kind of expressions. So we call it as expressions because we have a lot of operators which will be connecting the various components of the patterns. And then we have the finite automata, which is normally a device which is used for recognizing the regular languages. So one is the expression and another one is going to be the automata, which is a device or a machine which will be either in the form deterministic one or it is going to be the non-deterministic one. Not only the finite automata, we have another grammar which is coming under the formal language description. Generally grammar means the context free grammar. But we have a variant or a restricted version of the context free grammar. We call it as the regular grammar, and the regular grammar is the one which is normally used for describing the regular languages. So the rule format of the regular grammar is slightly differing from the context free grammar. Context free grammar is the most general one, but whereas in the case of regular grammar, we have restricted list of rules, like we can have that is A derives small a followed by capital B, or it is going to be A derives capital B is followed by a small a. So either we can have a single terminal followed by a single variable, or we can have a single variable followed by a single terminal. So in that case we will be calling the grammar as regular grammar. Another thing is the language, this is going to be general idea when we will be saying that a language is always going to be a regular language. Suppose you find out language itself is going to be the set of all strings. If the set of all strings is going to be finite, that is whenever you are given with a finite set of strings, irrespective of what the strings are all, definitely they are all coming under the regular languages, because any finite set of strings can be very easily described by using the regular expressions. So we need not bother about whether we have to go for a context free grammar or context sensitive, not necessary. You find whether it is going to be the finite set or not. If it is finite set, certainly the language is going to be a regular language. And you can see the various examples that are coming under the normally used as far as regular languages are concerned. It is going to be the set of all identifiers. Generally we will be using in the programming languages. You can say that A is an identifier, A2 is an identifier, or that is max total. These are all the various identifiers. So any identifier can be described by using the regular expression, or you can construct a finite automata for that. Similarly, you can have the constants. You can think about any constant like the integer, or it can be a string, or it can be a floating point number, whatever it is, they are all coming under the regular languages. Then you can think about the operators. Operators, you can think about the operators which are in C language or in C++. Maybe we can say that is plus is an operator. So whatever the regular expression required for describing such an operator is going to be exactly the same operator we need to use, because there won't be any replacement. But as far as the constants are concerned, we will be having a general pattern that is capable of identifying any constant. Maybe I can say that the digit is going to be a pattern. So in that case, the digit can be either 0 or 1 or anything up to that is 9. But I am writing the expression as some d star, as d plus. If it is d plus, then we can have one or more number of repetition of the digit that is d. So now it is a pattern which is capable of describing different set of strings. But whereas when you go for the operators list, the operator itself is used as the regular expression for describing the operator, because if I am saying the plus is an operator for addition, then there is no other replacement for that. Plus we have to use wherever we want to do addition. Similarly, that is less than. So we can use the less than operator for comparing two numbers. So this is what the another class of there is language which is coming under the regular. Then you can think about the data entry fields like dates, emails, then IP addresses, URLs. So these are all the various examples for the regular language. You can think about any date. It's having three different components like the day, month, and then year. Day itself is an integer. It's going to be a constant. Then month is a constant. Then another one, it is going to be the year. Then they are connected either by a small hyphen or a slash or a dot. So whatever be the case, it is possible to represent them with the help of regular expression. And then think about the IP address. It will be having four components. It's all bytes, just first byte, then dot, then second byte, dot, then third one, dot, then fourth one. So here we find that four number of integers. They will be there is concatenated just with the help of a dot operation. So when you are able to write a regular expression for an integer, then certainly we will be able to write a regular expression for that is four different integers. Just we are combining them with the help of some kind of operators like concatenation. But if you are having that is very large, there is any number of integers, then can be connected with the help of dot, then it is going to be like an expression, like a can be an expression, or a plus b can be an expression, or a plus b plus c can be an expression. So those kind of there is languages, those kind of strings cannot be described with the help of regular expressions. But whereas if you are sure that the integer is going to be repeated for 2 times or 5 times or even 100 times exactly, then we can represent them with the help of the regular expressions, or you can go for a finite automata. So that is what these kind of there is strings are like date or IP address or MAC address, and they are called the regular languages. So these are all the simple examples for regular languages. And now we have to see that is how we are describing the regular languages. Already I talked about that is regular expressions, and another one it is going to be the finite automata. And that is as far as regular expression is concerned, it is just like an expression kind of thing. But whereas in the case of finite automata, it is going to be a transition diagram, or it is going to be something like a transition table. But we are not saying that there will be only one method of representing the regular language, but we have different. So it can be a regular expression. From this diagram itself, we can see that regular expression is going to be a tool for describing the regular language. And then we have an arrow which is going to that is epsilon NFA. So NFA is a type of that is finite automata, that is non-deterministic inversion, and the non-determinism is because of the states where we have, that is the number of states that is in which the system can be available at any point of time. So if it is more than one, then certainly it is called an NFA, that is non-deterministic finite automata. And what this epsilon denotes, the epsilon denotes whether we have a transition for that is epsilon or an empty symbol or not. So if you have a transition for empty symbol, then it's called an epsilon NFA. The another one is called the non-deterministic finite automata. Whenever we write there is the NFA, it means that there is no question of having a transition for empty symbol. So here we have a transition for empty symbol, but whereas in the case of this NFA, we don't have a transition for NFA, there is epsilon or empty symbol. Then we can have another variant called deterministic finite automata. So it is, the difference is at any point of time the DFA or the system can be in at most one, that is stage. That is what we call it as deterministic finite automata. Then we have another variant of that, it is going to be the minimal state deterministic finite automata. So the finite automata, that is the word finite in the finite automata says that the number of states. So definitely we want to have finite number of states as far as any finite automata is concerned, whether it is going to be a deterministic version or it is going to be a non-deterministic version. So now the question is, in the case of finite, can we have 100 states for the same automata with another automata having similar like 50 or 70? So what they are all representing? If you are having an automata for some language L with 70 states, and if somebody else is coming with another automata for the same language with 100 states, definitely we will not go for an automata with 100 number of states. The question is, what is going to be the unique automata which is used for describing the language L? You can say that an automata is unique only if that is going to be the minimal state finite automata. So no question of having another automata with less than that states available in the given minimal finite automata. So is it possible to exactly find out the minimal state finite automata from the description of the language directly or not? So certainly it's going to be a very difficult job. That's what we are following this hierarchy. So we will start with regular expression, and then we have some algorithms like that is the Thompson's construction, which will be transforming the regular expressions into their equivalent epsilon NFA. Then from this epsilon NFA, if you want, you can go for the NFA, or you can directly go for the deterministic finite automata. So that's what the arrow marks are showing. So you can transform the epsilon NFA directly to a deterministic finite automata, or you can move it, convert it into NFA. Once it is transformed into NFA, we can transform it into deterministic finite automata by using algorithms called the subset construction algorithm. And the deterministic finite automata can be transformed into the minimal state automata just by using some kind of algorithms that will find out the equivalent states. And if you find that two states are equivalent in terms of the language recognition, then there is no need of having two different states. So they will be just merged, so that there will be a single state doing the job which is actually done by two or more number of states. So that equivalence, that is, if you find out the equivalent states, they can be simply removed to get the minimal state automata. And if you want, we can once again get back the regular expression from the minimal state deterministic finite automata. So that's why it is completely a cyclic process. You can start from the finite automata, you can go for the regular expression, or you can start from the regular expression, you can go for the finite automata. So anything can be done in a vice versa manner. So the arrow which is regular expression to deterministic finite automata can also be done. You can even directly start with deterministic finite automata also. So but directly constructing deterministic finite automata from the natural language description of the given language may not be a very easy job, but writing regular expression, then going to epsilon NFA, then going to the NFA, then finally it is going to be DFA or the minimal state DFA is going to be a natural that is way, and it is somewhat easier also. That's what we are following this strategy. But all of them are describing only the regular languages, whether it is regular expressions or minimal state finite automata or it is going to be NFA, they are all describing only the regular languages. So now what is the definition for the finite automata? So finite automata is a mathematical model of any system with discrete inputs and outputs. So it is going to be a model for, actually it is used for language recognition. We will be calling it as the mathematical model, and we go out to find out that how many states are there and what it is accepting and what it is going to produce as output. Generally it will accept finite number of symbols as input, and it will produce either yes or no as output. So that is what the meaning of the finite automata. So you will be having something like finite automata designed for recognizing the set of all that is strings with even length. Then every string which is given as input should have there is even number of symbols. If you have even number of symbols, the output produced by your finite automata is going to be that is yes, and if you are giving a string whose length is going to be odd, then the output produced by this finite automata is going to be that is no. So there is going to be a recognizer, and it is a model, and it will accept that is input having discrete number of symbols or finite number of symbols and producing either yes or no depending upon the presence of that string in the language of the finite automata or not. Let us go for a break, and after that we will continue the lecture. Welcome back after this break, and actually I was discussing what is finite automata. It is going to be a mathematical model with discrete inputs and outputs. The input can be any sequence of finite sequence of symbols, and the output is going to be either yes or no depending upon the presence of the string in the language of the finite automata or not. If it is there, it will give you yes, otherwise it will give you no. Now let us see that is what is going to be the detailed definition of the finite automata. So it is going to be that is quintuple. Actually it is having 5 different components. We will call A for, that is they use this notation, that is A for denoting the automata. We have the 5 components here, that is one is Q, then it is sigma, then it is going to be del, then it is starting state, that is Q naught, then it is going to be that is F, that is set of final states. So here we have the meaning of all these that is components as far as the finite automata is concerned. So the first one is going to be the Q. So what this Q is? Actually already I told that the finite automata denotes there will be finite number of states available. The states are actually used for showing that is the progress of the recognition process, whether we are in the initial stage or where we have reached the end of the finite automata, and what is the state in which currently we are. So based on that we will decide how much we have completed, or how much is the portion of the string which we have recognized, and how much is yet to be recognized. So that is it. So there should be finite number of states. Normally the states will be numbered with the Q0, Q1, Q2 up to Qn, or you can even number with 0, 1, 2, 3, etc. It is all depending upon the that is requirements. Based on that we can define and that is give naming for the states. But it should be very much that is clear that there should be only finite number of states. No question of having infinite number of states, because if you go for infinite number of states, the problem is you cannot implement such a system because it needs lot of resources, that is infinite amount of resources. Having infinite number of resources is certainly not possible. So if you want to implement a finite state, that is automata, then the number of states must be finite, so that you can write a program or you can design another recognizer, anything, it is possible. The next is going to be the that is sigma, which is the input set, or it is going to be the input symbols. So that is also going to be a finite set, because any language generated by the finite automata should be that is made from this sigma only. Suppose if the sigma is actually it is called as the alphabet. So sigma, if it is 0, 1, then you can think of any string which is in binary format. If it is going to be 0 to 9, you can think about any number with the symbols, that is digits from 0 to 9, or you can think about sigma is equal to A to Z. So you can think about any that is English sentence. So sigma is going to be the finite set from which the strings are all generated as far as the finite automata is concerned. The third one is going to be the very important one, which is the transition function. So the core functionality of the automata is defined only by the transition function. So it is having 2 inputs. You can see from this that is diagram, that is this representation. Del is a transition function which is having 2 inputs, that is it will take one input from the Q, that is a state, and another one from the alphabet, that is from the input alphabet, that is from sigma. And if you are giving these 2 as input for this transition function, it will produce another state as output. So actually it is the recognition process. If we are in a state and then we have to move to the next state depending upon the current input symbol. So we should know what is the current state, and we should know what is going to be the next, that is the symbol which we are having as far as your input is concerned. Just read that input and then find how that is we are moving, or what is going to be the progress, whether we will be moving to the next state, or we will be staying back in the same state, or we are going for the final state. It is all depending upon the transition function which is defined as far as the finite automata is concerned. The finite automata means the most important component of the finite automata is going to be the transition function with 2 inputs, and it is going to produce one output, and it is the definition exclusively meant for deterministic finite automata. It is not meant for the non-deterministic version or the transition function that is with the epsilon NFA, where the definition will be slightly differing. So here in the case of deterministic finite automata, one state is given as input for the first input, and one symbol that is going to second input, and it will give you one state as the output, that is going to be the output of the transition function. And the fourth component is going to be the starting state. So that is normally the place where the system is initially placed. So any system should start from an initial state, and what is that initial state? So it should be Q naught, we will be calling it as Q naught. And another important thing as far as starting state is concerned is, there should be unique starting state, no question of having more than one starting state. So we should have a single state that is designated start state, and that is a place where from we have to start all the recognition processes. And the fifth component of the finite automata is going to be the set of final states. So what is the significance of the final states? So if you want to recognize a string, we must start from the starting state, it is going to be unique, and we should reach at least one of the final state. So that is very important. We may have any number of final states, but the question is, are we able to reach one of the final state or not? If you are able to reach a state after writing all the symbols from the input, and if that state is designated as a final state, then we can say that the string is accepted. After reading all the symbols is very important. We may be able to reach the final state, but if we find that still some more symbols are available in the input buffer, then we cannot say that the string is accepted. Two conditions are very important. You have to ensure that the buffer does not have any symbol more, and another thing is we are in a state which is in F. So if both the conditions are matched, then immediately we can say that the string is accepted by the finite automata. So here we have a simple example for finite automata. Actually it is meant for recognizing the commands as far as C and C++ languages are concerned. So there is a starting state which is having, that is the symbol that is start, and this is going to be the specification or the name for a state, that is none. It means that nothing is recognized as far as the initial stage is concerned, there is no commands are recognized. And then suppose if you are having a slash, then we are moving to a state where which is named as slash, and if it is another slash, then we will go for another, that is state called named as C++. What does it mean? It is we have recognized two number of slashes. That is going to be the beginning of a command as far as C++ is concerned. But in the same time, if it is going to be a slash followed by a star, then it is required that we must have a star followed by a slash. So if you find anything other than that is the star slash, then it will be looping in this statement. So and after that, if you find that star, then once again it is going to be a slash, then we will come back there saying that there is a command has been recognized. The starting of the command is recognized by either by slash in C++ or a slash followed by a star as far as C is concerned. So this is the principle, that is whatever is available in the circles, they are called the states, and the transitions. So we have a state called none and we have another state called slash, and they are connected by an arrow, that is called the edge, or we call it as a transition. And what is its label? So every transition must have a label. If you do not have a label, then it is not going to be a meaningful transition. There can be even that is more than one label also. Suppose if I am having a label that is slash followed by a comma, then it means that we can have a command starting with a slash, or you can have a command starting with a comma or a single quote. So it is possible to have more than one label in a transition, but at least one label is mandatory as far as any finite automata is concerned. Then we will be having there is a state, like suppose if you want to represent the states which are final, we will be using the double circles. So here we have that is the next one, that is called the transition function, which is normally used for recognizing strings. So finite automata is used for recognizing strings, but the transition function whatever we have seen is meant for, that is accepting one symbol. But if you are talking about strings, there will be more than one symbol. That is going to be a finite sequence of symbols constitute a string. So now the question is, how do you pass a string as input for a transition function? So as far as del is concerned, it will accept one symbol at a time, but we have a transition function called the extended transition function, which will accept any sequence, finite sequence of symbols. So you start from q0 and you find out what is going to be the string of symbols, and after accepting all the string of symbols available in the given string, then what is the place where we are, or what is the state where we are, and that will tell you about whether the string is recognized or not. Here you can see the definition for the extended transition function. It is called del cap. It takes a state that is q and a string that is w and returns another state called p. So one state it is important, and another one is going to be the string, which is either it can be an empty string or it can be a string of finite number of symbols. Then what is going to be the output? It is going to give you an output that is called p. So when you are talking about the definition for the that is extended transition function, it is like q cross sigma star. Sigma star, I mean sigma means it is going to be a single symbol, and if it is going to be sigma star, then it is going to be any number of symbols, that is going to be a string, and it will produce another state as output. Another state, I mean that is a single state. So what is going to be the basic definition or basis where from we will start? So, it is going to be del cap of q comma epsilon is going to be q. It means that epsilon, that is a string which with no symbols, cannot change the state. So, no input and no change of state. And what will happen for the induction, there is induction, that is how it is recursively used for recognizing the strings. You can say that there is a string, there is w is given for you, and it has a split of, that is xa. It means that x can have any number of symbols, and a is going to be the very last symbol available in w. The question how we are recursively defining that is, first of all you find out the transition for x, that will be once again recursively defined. That process will be repeatedly done until we find that x becomes epsilon. Whenever x becomes epsilon, then immediately we can say that this q will never change, that is del cap of q comma epsilon is going to be q, and then we can keep on evaluating the transitions with the help of the transition function, that is del, because del is already given as far as the finite automata is concerned. So, we start with, that is del cap of q comma x. Once it is evaluated, from that state you find out what is going to be the transition for the symbol, that is a, which is going to be the last symbol available as far as this w is concerned. Here the conditions, a must be belonging to, that is sigma, and x belongs to, that is sigma star. It is going to be a, that is a recursive definition for the transition function, that is we call it as extended transition function of the deterministic finite automata. Once again it is differing for the non-deterministic finite automata version. Here we have the definition of the language. The definition of any language, that is going to be like the set of all strings. The set of all strings, I mean, that is any string which is accepted by the finite automata. So, what we should do here is, you find out that is the set of all strings, that is x, and we will be having, that is the del cap, that is transition function, extended transition function. You start from q naught, that is certainly going to be the starting state of the system, and then you accept the entire symbols available in x. Now, you find out what we are getting is the resulting state. Suppose if you are getting the resulting state, that is which is in f, then we can say that the string x is accepted. If the resulting string x is, that is a resulting string, that is a resulting state after applying, that is x from q naught is not in f, then the string x is not accepted. The other conditions here, q naught must be a starting state and x must belongs to sigma star, because it is going to have symbols only from the alphabet defined for the deterministic finite language. So, that is how we are defining the deterministic finite automata language. So, here we have seen that is actually the recognition, actually this string, that is where extended transition function is used for defining the various language or mean the various strings. But if it is going to be a simple transition function, it is actually used for defining the various symbols available in the finite automata. So, here is a summary of the lecture. We have seen what is regular language. It is a basic class of language as far as Chomsky hierarchy is concerned. Then how the regular languages are described with the help of either finite automata or regular language, the regular expression, or whether in the NFA or DFA version, and the definition for deterministic finite automata we have seen, and that is how we are going to define or recognize strings. It is with the help of the extended transition functions for the finite automata. We have few questions as far as this topic is concerned. The definition for regular language, and maybe we will be asked to give some examples for that. The examples, like you can very easily quote examples from the programming languages, the keywords are the regular languages, then operators, then the constants, then in general scenario you can think about the date, then the complex number, that is also going to be a that is, even though it looks like an expression, it is having only the finite number of components as far as any complex number is concerned. So, it is going to be a regular language. Another question is, that is how the strings are all processed using the deterministic finite automata. We have to go for the extended transition function. By using that, you find whether the final state which you are getting is going to be the that is in f or not, then it is going to be the string accepted. Then what are the various tools used for describing regular languages, like the finite automata, or it is going to be the regular expression. The finite automata can be even be in the deterministic version or in the non-deterministic version, or it can even go for the minimal state finite automata. So, with this I conclude this lecture. Thank you all.